I want to thank the organizers for inviting me to give these talks. It's going to be a challenge to give first talk after lunch. So please ask questions to keep everybody awake. And I think I probably have much more material than I can present at a comfortable pace. So I will be looking for Sasha's reaction and slow down if he looks confused. Okay.
I understand that everyone. Yeah, but the question.
You already have a question.
No. I have a request. After you answer some question from the audience, please repeat the question.
Repeat the question.
Because it's recorded, and then.
Got it. Thank you. So I'll be talking about pseudorandomness from hardness, and I'll try to give you some idea of the connection between these two notions. There are lots of objects that you can call pseudorandom, kind of with intuitive definition of what pseudorandom might mean. So one working definition could be, it's an object which shares properties satisfied by random objects. So if you pick something at random, it will have the property with high probability. And then you want to find an object like that without picking it at random, but using deterministic efficient procedure and algorithm to find it. Some examples of pseudorandom objects include expander graphs, error-correcting codes, and you don't need to know what those things mean. Although I think Marius will talk about expander graphs maybe tomorrow evening, so you'll hear more about it in his talk. And also incompressible strings. Think about Boolean functions of high circuit complexity, or time-bound Kolmogorov incompressible strings that you may want to find efficiently algorithmically somehow. And the main focus of my tutorial will be pseudorandom generators, or PRGs, which kind of distributions which look like uniform distributions without being uniform distributions, like very sparse support and also efficiently computable or sampleable from. And the main insight from the 80s was that essentially pseudorandomness and hardness are equivalent. So I'll try to give you some idea about this connection. And my ambitious plan is to go through these items, like talk about PRGs, classical distinguisher into next bit predictor, algorithm due to Andy Yao, hybrid arguments, Nissan-Wigderson generator, and then as applications, two ways to use generators: use them to win or use them to lose. So play to win and play to lose are both important. And I hope to give you an idea, the applications where it comes up, where you want to win, where you want to lose. So let me start with a definition of a PRG. So this is a mapping from L bits to K bits. And you think of L as being smaller than K because you want to stretch a short, truly random string of length L into something much longer, which of course is not completely random anymore, but may not be maybe indistinguishable from truly random. And indistinguishable is for whom? So you have a class of tests, which you think of as efficient algorithms or circuits of small size, that look at the outputs of the generator and are fooled by the generator, epsilon fooled by the generator, if they cannot tell the difference between the outputs of the generator on the one hand and the uniform distribution on the other hand. Okay? So the difference between the statistical behavior of your efficient algorithm C, of test C, on the uniform distribution versus the pseudorandom distribution is negligible. It's like epsilon, smaller than epsilon. So far, so good, Sasha?
Yeah, no.
Good. Okay. And so the task is, given a class of tests that you want to fool, construct a pseudorandom generator that will be fooling those tests from the class. And you can think of class of tests as abstractly, like any collection of functions that you may have a desire to fool for whatever motives you may have for that class of functions, Or more generally, it can be like a class of small circuit computable functions. So easy functions in the sense that they're all computable by small circuits. So we want to fool a class of small circuits. As I already mentioned, you want a large stretch. So you're pretty greedy and you want to output lots of fake random strings, pseudorandom strings, long pseudorandom strings at the cost of very small investment in true randomness. And another piece of terminology that I'm going to be using is a notion of an epsilon distinguisher. So a test D stands for distinguisher, which is not fooled by the generator G, is going to be called a distinguisher for that generator. Okay, it satisfies the opposite of the property that you want when you fooled. So a distinguisher will tell apart the uniform distribution of Z's here from the pseudorandom distributions of the outputs of the generator here. And epsilon is like how good this distinguisher is, by how much far apart he tells this distributions uniform and pseudorandom. Okay, so if the generator is good, there are no distinguishers. And if the generator is broken, it's not good, that must be because there exists some distinguisher for that generator. Okay, so I defined the notion of a generator, pseudorandom generator. Now let's try to construct one. And I should have mentioned that the examples of pseudorandom objects that I mentioned before, like expanders, error-correcting codes, we have decent amount of success in constructing efficiently, explicitly. But for the two remaining items on my list, hard Boolean functions and PRGs, we don't have much success. And this is because those two last objects talked about computational complexity, about circuit complexity in particular, and we don't have much success understanding circuit complexity. So we have conditional results, building pseudorandom generators in particular from the assumption that you have hardness. And this is exactly what I'm going to try to explain to you. So let's start with a very simple kind of baby example where I have a function f, which is a Boolean function from n bits to 1 bit. And let me be vague, but call it a hard function to compute. What exactly this means will become clear in a moment when we'll see what kind of properties we want from that function to be useful in the construction of the generator. The way I'm going to define a generator using this function f is as follows. A generator will extend the seed x, which is an n-bit string, by 1 bit, which is the value of the function f on that input x. So the generator on x outputs x itself as is, and outputs 1 extra bit, which is the value of the function f on x. So this generator has some stretch, it's non-trivial, goes from n bits to n plus 1 bits. It's pretty poor stretch, but it's non-trivial. And so let's see under what conditions on f this generator will actually be secure, will actually be pseudorandom generator. So let's suppose that this construction is not good. Suppose G is not a PRG for a class C of some tests, which means by the definition of not being good that there's a distinguisher, call it D, which distinguishes the outputs of the generator distribution from the truly uniform distribution with some nice parameter epsilon. Think of epsilon as a constant. You don't need to think about epsilon as something else. 1/3, say. Okay. So being very explicit, I'm trying to go very slowly. So being very explicit here, let me replace g of x by its definition. So d is given as input in the first term here, x and f of x. And here, d is given truly uniform input, which I decompose into x and a random bit b, where b is independent of x. Piece of notation that I'll be using occasionally is u sub n refers to the uniform distribution on n-bit strings. So by looking at the second inequality here, you see that D is biased towards strings which have as last bit the value f of x. Okay? So there's a little bit more probability mass that D places on strings x comma f of x than strings x comma random bit. So you'll have a little bit of bias towards f of x. And we're going to exploit that by designing an algorithm. This is a construction due to Andy Yao that will try to compute f of x given a distinguisher D. And so notationally, I'll say that A has access to this distinguisher D, uses it as an oracle, and will try to compute f of x. And the idea of the algorithm is very simple. The algorithm is 3 lines. You pick a random bit, r, and so given x, you want to compute f of x. So given x, you pick a random bit r, plug it into D as the last bit, and see if D says 1. If so, you output a random bit r, otherwise you output a negation of random bit r. Okay? And the claim is that I'm going to prove, or at least wave my hands, try to prove that, is that this algorithm I just defined is pretty good. The probability that this algorithm A superscript D is correct on computing f minus 1/2 is exactly the distinguishing probability, the difference between the probability D accepting on the pseudorandom distribution versus the random truly uniform distribution. And remember, this bottom difference was like epsilon, it was large. So assuming we prove this, which I'll do in a moment, we'll show that the correctness probability of my algorithm A superscript D will be at least 1/2 plus epsilon. So it's better than 50%. Okay? Any questions so far? Okay, so to prove this equality, so equalities. Mike Sachs once was giving a talk and he said, equalities are easy to prove because they're equalities. The inequality that give you problems, because then it's not exact. But if it's exact, you just plug things in and it works out. So to prove this equality, you can do it the hard way or the easy way. I'll try to show you the easy way, hopefully. This is probability over all possible x's, and we'll prove it, like think of probability over x as like expectation over x's, and you want to prove this equality of the two expectations, so we'll prove it term by term. In other words, I will condition on x. So fix an x, okay? And then you have two cases to consider for this fixed x. Either this D on x does not depend on the last bit, so D of x0 is the same as D of x1, or it does depend on that bit, which means that because D is Boolean, that is flipped, when D of x0 is the opposite of dx1. Okay, those are the two possibilities. In each of those two possibilities, we'll show that you have equality between these two expressions. Okay, let's do that. So suppose we, in case 1, that D does not care about the last bit. Then whatever it does here, it will do there, because B is not important. All right? So this difference of the bottom two terms will be 0. What about this term here? It's not hard to see by the definition of the algorithm that if D does not depend on the last bit, then my algorithm AD will always output a uniformly random bit as the answer. Okay? You can convince yourself by just staring at this three-line definition of the algorithm. Okay? Which means that the probability that the random bit is equal to f of x is, of course, exactly 1/2. And 1/2 minus 1/2 is 0. So you have 0 equals 0 in the case 1. Are you with me so far? Case 2. So in case 2, the second probability in the bottom will be exactly 1/2, because D accepts one B and rejects the other B. So you have equality here, making progress. And this expression will be exactly equal to that expression by the definition of the algorithm AD. AD will be correct exactly if D on x comma f of x is 1. Okay, it may take like a second to process this, but this is true statement. Maybe too much after lunch, but is that okay?
So you consider deterministic?
Yeah, D is deterministic, yes. Yes.
But that's probably true for non-deterministic.
Yeah, for randomized, yeah. You can generalize, I'm pretty sure, but like, it's simpler to consider a deterministic case. But the algorithm that we get from deterministic D is going to be the randomized algorithm. AD is randomized because I pick randomness, one bit of randomness. Okay. Yeah, you will be fixing quite a bit of randomness, and we'll pushing it in the advice, non-uniform advice of our algorithms. Okay, but yeah, for now, just randomized algorithm or deterministic algorithm. So once we verify this claim, we get that if there's a distinguisher for my naive generator with extends by one bit only, then the function upon which this generator was based can be predicted on half plus epsilon fraction of inputs, which means that this function is somewhat easy on average under the uniform distribution. The contrapositive would be that if I start with a function f, which cannot be predicted like that, my generator construction will work. It cannot be broken. Okay? So the upshot is that if you start with a function f, which is sufficiently hard on average for some class of tests, and by sufficiently hard, I mean it's hard to predict it better than half plus some small amount, then if I use this function in the construction of my generator, I'll get a generator which fools all the tests with the property that a to the d, where a is the algorithm described above, and d is my test that is not fooled by this generator. If this algorithm a to the d is in a class C, then I have a contradiction because by my assumption, all script C tests cannot compute f very well. Okay. So if I have a hard function with respect to some class of function, some class of algorithms, then with respect to related class of tests, I have a PRG which is not broken. Any question?
Somehow you said that the PRG should be easy to compute, but this is not the case.
Well, yeah, F is like average case hard for circuits. Yeah, so this G is not particularly exciting in the sense of efficiency, but it is a non-trivial one-bit extender. So in that sense, it like goes in the right direction, but we're not done yet. Yes. So more work needs to be done. Exactly. So let's move on. You can think about this classes of tests very abstractly, but let's just, for concreteness, think about circuit classes of different circuit sizes. And you can think of exponential size circuits for the class of functions, for the class of algorithms with respect to which your function is hard, and slightly smaller class of circuits to the n over 20 rather than to the n over 10 for the distinguisher. So if you have hardness against exponential size circuits like of size to the n to the 10, then you get pseudorandomness with respect to a class of test of slightly smaller size. And these are kind of trade-offs that you normally get. So to get pseudorandomness with respect to a certain class of tests, you need to go to slightly more sophisticated, more powerful class of algorithms and get your function which is hard with respect to that first.
So you don't assume that we know how to construct a function in the first
No.
class?
No, I'm just saying that if function f were hard, then this generator construction would work. And this gives you first approximation to the idea that you can convert hardness into pseudorandomness. Okay. However, so far, it's lacking in many respects. In particular, the stretch is very poor. And you go just from n bits to n plus 1, so the additive one bit is like laughable. So we want to get polynomial stretch, where you go from n to some polynomial in n. Or even better, you go to exponential stretch, where you go from n to something like 2 to the n. Okay, and that's our final goal, to get a generator with exponential stretch. First thing, we'll try the following somewhat naive idea, but is already non-trivial, and will help me to illustrate one important point of pseudorandomness, hybrid argument. So let's consider the following construction. Rather than a single input, I have k inputs. So each one of the xi's is an n-bit string, and I have k of them. And my generator will output all the inputs, x1 through xk, and then evaluations of f on each one of them. And you get from 1-bit extender, k-bit extender. Why does it work? Okay, basically, we can reduce to the case we analyzed earlier, where we showed that there will be a distinguisher which can be converted into a predictor by Yau's algorithm. Now we have a bunch of occurrences of the function f in our distribution output by the generator, so we're not sure which occurrence out of those k occurrences we're going to predict. And this is where the following hybrid argument will come and help us. So let's assume that this construction, to prove it's correct, assume it's not. Assume G is not a PRG, which means that there is a distinguisher D for some epsilon, like 1/3, where D tells output of G from the uniform distribution with difference epsilon. Let me write a bunch of lines, starting with the definition of the generator G first. So x arrow represents a tuple x1 through xk, just for notational convenience. So I have x arrow fx1 fxk, which will be called distribution q0, which is exactly the distribution of the generator G. And then I will be slowly replacing from the right the f values by the uniform bits, uniformly random bits. So my q1 will be, I replace the last rightmost bit by uniform random, then q2 replace the last 2 bits by uniformly random independent bits, and so forth. And the kth distribution qk will be replacing all the f's by the uniformly random bits. So I make k steps to go from top to bottom. And then I do a simple trick by writing this difference between behavior of distinguisher D on Q0, which is, remember, G, and behavior of D on QK, which is the uniform distribution. I know that DQ0 minus DQK is large, and I'll just write the sum by alternating minus plus, going through my intermediate distributions in this argument. You see that all of these terms cancel, and I only have leftmost and the rightmost remaining. So very simple mathematical trick. But then by averaging, you know that if I have a bunch of these terms and their sum is bigger than epsilon, and there are k of them, then there must exist at least one that is as big as epsilon over k. Yes? And any I between 0 and k could be the index, but for the sake of presentation, for simplicity, I'll assume that I is equal to 0. So then I have that these two distributions differ by epsilon over k as far as distinguisher D is concerned. And now the green part is the inessential part. The distributions D differ in the last position, where the first one has f value and the second one is a random bit. The green part does not, is completely independent of the action happening on the input xk. So as Bruno suggested, we can fix the inessential parts, the ones in green, by an averaging argument so that preserve this inequality. Because the expectation is large, there is a setting of the values that will preserve this expectation after the fixing. And so we sweep under the rug all these green things, we'll hardwire them into the distinguisher D. That will make it a bit more non-uniform, but that's okay. And we're left with a new algorithm, like if you ignore the green stuff now, you get to the case we analyzed before. You have single x and f of x, single x and random bit. And Yau's algorithm can be applied now, and it will give you a predictor from this distinguisher with a bunch of things hardwired.
And
It's not important that f can be complicated
No.
because it's fixed.
Exactly, exactly. Right now, once x's are fixed, f of x's are also fixed to just bits. So we completely ignore the f, and the complexity of f does not enter into the complexity of the advice. It's just a bit.
So it's essentially non-uniform.
It's a non-uniform argument, correct. Okay, so one thing I want to point out here is the predictor you get the same way as before with this non-uniform advice for green stuff being hardwired is going to have success probability in computing f at least 1/2 plus epsilon over k. So you'll have a little bit of decay here. Before it was epsilon, now it's epsilon over k. So the more stretch you want, the less better than 1/2 you'll get the predictor for, which means in the contrapositive, you need to start with a harder function f in order to get a longer stretch k, which kind of intuitively makes sense. If you want to get more, you need to start with something better. Okay? Good? I'm going pretty fast. Is that okay?
So just who believes he understands more or less what is happening?
Wow. Okay, thank you, Sasha. Do you understand?
I believe that I understand.
You believe. Okay. All right, so now I'm going to show you, and probably many of you have seen it, but if you haven't seen this, this is one of the gems of pseudorandomness, this construction of Nisan-Wigderson generators, which starts with this naive generator that I just explained to you earlier, the one here, and solves the obvious problem. What's the problem here? We use lots of independent xi's to output only k new bits. So we invest lots of randomness to get very little new pseudorandomness out. It would be really nice if we didn't have to use x1 through xk as completely independent k n-bit strings, but instead maybe start with something like of size, say, n square, and stretch it out to k tuple of n-bit strings, and then apply this construction to that tuple of x1 through xk, which are not completely independent, but came from something small, short to begin with. Okay? In other words, we want to kind of de-randomize this construction and have some small string that can be stretched to this tuple of k n-bit strings, and then hope that whatever we said here will still work in this de-randomized setting. And this is exactly what Nisan and Wigderson did. And they used a nice combinatorial construction of so-called Nisan-Wigderson designs to get this stretching from small string into a k tuple of n-bit strings. And so the idea is you start with some new seed z of some length L, and we'll try to make L really small as we can get. And you partition, not partition, but you define a bunch of substrings. They don't have to be contiguous. So just for the sake of this picture, it looks like they're contiguous, but can be all over the place. And you want to get as many of them as possible. So each blue circle here corresponds to one way of extracting one particular substring from the seed Z. And you want to get like k of them, and we want to maximize k. And we'll see that we can make k exponentially big. And the property you want is that any two substrings have very small overlap. And this is generalization from what we had before, where the overlap was 0. They were completely disjoint. And now, at the expense of allowing a smallish overlap, you'll be able to pack in a string of length n, like exponentially many in n strings like that, with smallish overlap. And that will give us the exponential stretch generator that we're after. Okay. So how we define the generator? Once we have this partition or this definition of substrings from Z, then we just apply f to each one of those. And so the generator is defined given this system of sets that I'm going to talk about in a moment. S1 through Sk, this design, collection of sets with small pairwise overlap. A seed Z is mapped to the value of the function f on seed restricted to the first set, which is the first substring, second subset, and so forth, k times. Is that clear?
So in this picture, actually the bottom part is much larger.
Yeah.
It's just
The picture is not to scale. Yeah, and it's not even correct relatively, because the bottom part is much longer than the top part, because they have a huge stretch. Yeah, thank you. Where do we get this collection of sets that pack so tightly, and so many of them can be packed into a small string? Well, you can prove this combinatorial statement, and this is a theorem that I have here. I'm not going to prove it, but let's just go through the statement. It basically says that if you choose your parameters n and gamma, then you can have a seed of length L, where L is going to be something small, like n squared over d, where d is the parameter of overlap. So any two distinct sets have common part of size at most d, which will be at most gamma log k, and k is the number of sets that you output. So I'll just let you read the statement. Intuitively, it says that if you allow non-trivial overlap, you can pack a lot of mutually almost disjoint sets. And how many of them? Like, you can go exponentially big. And the seed length L will be dependent on the amount of overlap that you're allowing. Okay? And for us, the interesting setting of parameters, well, d will be roughly linear in n. So if d is like gamma n, then n squared over gamma n will be n, and so L will be linear in n, and the number of sets that you'll output will be, k will be exponential in n. Okay, so if I have the setting of parameters here, yes, in the example, so the interesting setting of parameters is that you output exponentially many sets, so k, the number of sets, is like exponential in n, then according to this theorem, you get these parameters. The seed will be linear in n, and so you get exponential stretch that I promised you. You go from a seed of length roughly n to number of bits, which is exponential in n. All because of the existence of this set. Yeah, question.
Quite interesting. D is the allowed overlap.
Yes.
And n is the size of the S.
Yes.
If
So
D is roughly n, then it means that they overlap a lot.
they overlap like a constant fraction of n,
Okay, constant.
like n over a million. Yeah. So, I mean, nothing is for free. Should I repeat the question? So the question was, what's the relationship of the overlap and the sizes of the set? Because we're so greedy that we want to pack exponentially many sets, we need to allow quite a large overlap. Okay, so if I allow overlap n over a million, then I can get to the n roughly sets like that. If my overlap is much smaller than that, then I cannot have as many sets. And these parameters in the theorem tell you like what you can expect depending on how much overlap you're willing to allow. Okay, so you can play with those parameters.
And you need an explicit construction.
You need an explicit construction, yes, because yes, now we're getting back to your question, how explicit the generator is. So before it was not explicit, but now it's getting more explicit. There's still an issue of like, where do you get this f from? But ignoring that, you definitely need to construct these designs so that you can actually apply the scheme to your given f and map the seed into like exponentially many output pseudorandom bits. And fortunately, this collection of sets can be constructed deterministically efficiently in this time, if you're really smart, and if you're a bit lazy, in this time. Okay, both times are okay from the point of view of exponential stretch, but if you like want to look at the intermediate parameters, then this is probably preferable to that.
And for that, you don't need expanders or some. So it's
No, it's much simpler. So for this bound, so first of all, how do you argue first non-constructively that this thing exists? Use a random method. pick the sets randomly and argue that with decent probability, they will satisfy the properties you want. Because if you have a random set, you take another random set, chances that they overlap by a lot is pretty small. Okay? Once you know the existence of such a set system, then you can do like brute force algorithm, greedy algorithm, and find sets one by one, so that each next one does not have much overlap with all the previous ones. And because you know that they exist, your greedy algorithm will succeed, and the runtime will be 2 to the L, because this is how many sets you may have to try in your brute force looking for the next set. Because the universe is of size L, so there are 2 to the L subsets, and you try them all.
But how the existence makes greedy algorithm possible?
Because by existence, you know that you'll find something. It exists.
But greedy algorithm can go in the wrong direction and then it doesn't.
No, greedy algorithm will find the next good set with the property that it's small and it does not have large overlap with any of the previously found sets.
So the existence is modular conditional to any previously found set.
Yes, yes. Yes. As long as you don't, so the probabilistic argument tells you that as long as you don't choose too many sets that you want to get, they will always exist with small pairwise overlap. Yes? If you're too greedy and if you try to pick too many sets, then the probabilities will not work out. Those set systems will not exist. But if you choose the parameters not too big, then with high probability, your randomized construction will work, and then you can randomize it either by brute force greedy algorithm or using method of conditional expectations and using some Chernow bound expressions, and a little bit more complicated, but you'll get better runtime. Polynomial in k, L rather than exponential in L. But this is not important for this talk, it's just for the experts. If in case you need to use those things sometime, then they are better than this brute force greedy algorithm that I explained. And the interesting choice of parameters, that's why we had to go through this trouble, because we wanted to have exponential stretch, and if you choose k to be something like 2 to the gamma n, then the universe size L by the theorem will be like n squared over gamma n, which will be like n. So you have seed size of length n, and you output to the gamma n pseudorandom bits. That's your exponential stretch. So you're very happy. Good? Any questions so far?
It's difficult to follow all the parameters, but general scheme is more or less key.
Like,
with K, Alex.
The parameters are a mess, but the intuition is like, it makes sense that if you allow small pairwise overlaps, then it's possible to have more strings packed into a short string, right? And then you just work out the numbers and you get the theorem that I stated. I don't expect you to see why this parameters particularly work. You need to do some calculations for that. Okay. One thing I didn't tell you yet is that this construction actually works, because we analyzed this kind of independent construction, non-derandomized construction in our previous attempt, and now where the inputs to F's were all independent, and now the inputs to F come from this short string and they have some pairwise overlaps. So things change, so we need to do a new proof of security analysis of pseudorandomness properties of the generator. So let's do that. So we already know what to do. We assume that PRG is broken by some distinguisher D. So we have this difference between the pseudorandom distribution and the uniform distribution bigger than epsilon. We already have seen the hybrid argument, so we're going to apply it and say, hey, there will be some position I where I'll be able to tell the difference between pseudorandom and uniform. And here I say, okay, I is the position, so the difference will be exhibited here in the ith position, where my first distribution and second distribution have the same stuff before this position. Then in this position, I have F on the top and random bit B at the bottom, and the rest are all random bits. And this is all the same. These are green stuff are the same in the top and the bottom. So the action is happening right here in the ith place. And now we try to do the same thing that we did before by sweeping things under the rug and fixing things by averaging. And let's see how far we can get with that simple idea. Let's handle the easy case first. Those green beads are just 1 bits among friends. We can fix them, and we don't pay much, just k bits, right? So we can fix this by averaging and just forget about this green stuff using non-uniformity. Okay, then we'll try to handle this part here, the z's. Now, the only z that we want to keep free is the z restricted to set Si, because that's where the action is happening. Remember, z is kind of longest string, and Si picks a substring from z, and there's some other stuff in z. That other stuff in z, outside Si, we can just fix by averaging and preserve this inequality bigger than epsilon that we had. So far, so good. We're just fixing things by averaging argument and preserve the inequality, so we're very happy. There are still these things here, f's on z restricted to S1, z restricted to S2, and so forth, z restricted to Si minus 1. So now we want to fix these guys. And they're not quite fixed yet. Why?
Because there is free intersection.
There's intersections, exactly. But the good news is that intersections are small. Therefore, they're almost fixed. Let's see how much almost is. Well, any two sets depend on something like allowed overlap. And remember, allowed overlap was like gamma n for some tiny gamma, like 1/1,000,000. Okay? So each of those functions after the restriction depends only on gamma n input bits. So you can just hardwire the whole truth table of that function on gamma n bits. How much size do you need? 2 to the gamma n. It's bad, but we're working in the exponential regime, so it's actually okay. So gamma is small enough, so 2 to the gamma n will be sufficiently smaller than 2 to the n, which is like a trivial bound, so we're still winning. We're still doing something good. Okay, so now the bits of advice we need will not be 1 bit as before. Remember, Sasha, your question? Before it was 1 bit of advice per each of these f's. Now it will be 2 to the gamma n bits of advice per each one of them. So we pay more, but we think we try to keep things under control. So the total amount of advice is still going to be exponential, but non-trivially smaller than the trivial to the n bound. So we still win. Total amount of advice will be something like 2 to the gamma n. And if you make gamma small enough, it will be sufficiently smaller than 2 to the n, so that you say that there's going to be a predictor. Yeah, so the upshot of all this is the following. If I start with a function f, which is sufficiently hard, it cannot be computed on more than half plus epsilon over 2 to the gamma n. So the advantage over a half is really exponentially small, but it's non-trivial exponential. It's not like 2 to the n, it's 2 to the gamma n. So which means that it's feasible, it's possible to get that. Okay, it cannot be ruled out. So if you have this function with such exponential hardness, average case hardness, by circuits of also exponential size, and there's some dependence between this advantage and the circuit size, then the NW generator based on this function with exponentially many sets in my design will work. Will be a PRG that will fool linear size circuits. And the reason it will work is that if there was a distinguisher of linear size, then by hardwiring into it this advice of this much size, you would get a predictor for the function with this kind of advantage, which would be a contradiction.
Linear allowing 2 to the gamma n.
Yes, linear in the output of the generator, which is like exponential, huge. There was a hand? Yeah.
Please say again where the 3 times gamma comes from.
Oh, this is just like my overestimate of like putting all the advice. You have 2 to the gamma n bits for string. How many of them do you have? You have k sets. K was set to be 2 to the gamma n. So this is already 2 to the twice gamma n. And just to be safe, I'll throw in 3. Because there's some other advice that I told you, but you forgot, so, but it's safe, yeah. Make sense?
So how the total advice is taken into account in the argument? So where it's becomes
So the total advice will be added to the distinguisher D to get the predictor. So the size of the circuit to compute the function on average will be a function of the size of the distinguisher D you start with, plus the additional advice you need to hardwire non-uniformly into that distinguisher. So the distinguisher you start with is linear in the output size of the generator, which is like 2 to the gamma n. So you start with a circuit of size 2 to the gamma n, and then you add to it advice of size roughly 2 to the gamma n. So all in all, it still remains like 2 to the gamma n size circuit, which computes the function f kind of well on average. And if you start with the function f, which cannot be computed like that, you get a contradiction, and so your generator based on that hard f works. Does that make sense? Any other questions so far? Okay. Yeah, so this, you can always rescale things, and if going from n bits to 2 to the gamma n sounds confusing, usually people state the generator as, like rescaling things, as going from a seed of length big O of log n to n pseudorandom bits, and this generator is pseudorandom, secure against tests computable by linear size circuits, linear in the output size, linear in n. And it's equivalent to what I just said, but just rescaling exponential to linear, renaming things appropriately.
So it's security and complexity of computation. G is what after the scaling?
Okay, yes. So that's the next thing, exactly. So let's suppose that we have this hard function f computable in exponential time. Then the complexity of computing the generator G will be exponential in the seed, which is only polynomial in the output size, because the output is exponentially bigger. Okay, so let's make sure that we see that. So if my function f is computable in exponential time, and my seed is of length log n, then I need to evaluate this function on log n bit things to get my k values of f. Each one of them costs me exponential in log n, which is polynomial in n, and I do it n times. So overall, my time is polynomial in n to compute my generator. Okay. So if my function f is computable in exponential time, the time complexity of computing the generator is polynomial in its output, polynomial in n, if generator goes from log n bits to n bits.
Sorry.
Yes, please.
There's something I didn't understand. So could you clarify what the difference is between setting bits to a fixed value and providing their values as advice?
It's the same thing. So when I fix bits, then I need to tell my distinguisher D what those bits were fixed to. So they're particular.
I mean, the ones that get fixed in the blue line are the majority, right? That's 1 minus gamma fraction that gets fixed. And there's a gamma fraction that remains unfixed.
No, I guess there the confusion is that if you fix bit, you decrease the size of the circuit, not increase.
Not necessarily. If you have a big circuit and you fix some of its inputs, you don't necessarily simplify the circuit to something smaller.
But it doesn't become bigger.
It does not become bigger, yes. Yes, yes.
But here it becomes, because you need to encode the circuits which compute this boundary.
Yes, okay. Oh, I see. I see.
More, something more.
Yeah, so like if you go back to this Yau's algorithm, AD, let me find this. Yeah, this 3-line definition of the algorithm. Did I go past it? Okay. It's here, okay. Yeah, so this algorithm, so we'll try to predict the value of the function f, which is on some input x. So it will run the distinguisher which has a longer z, where x is sitting in some particular place, and the rest of the stuff are fixed non-uniformly. And then it will have to compute the fixings of other f's on a given x. Remember, the x is like this free stuff that was not fixed, And so my restrictions of f's on the previous positions have some overlap with this x. And I have truth tables that I hardwired that I can use to look up the value of the function, of the restricted function that I need to plug in into D and then run it. Okay?
So somehow you include in hardware
Yes.
the circuit which computes the restriction of f.
Correct. Correct.
You somehow say that it's fixing bits, but then it's fixing
No, it's like,
something universal.
yeah. I have this huge strings that will be part of my circuitry, and my circuitry will have access to those bits and use them as it needs to. And I'm trying to explain that the way it will need it, once x is given, it will have to go and look up which values of the restricted functions f it needs to plug in appropriate locations other than the non-fixed one, and that comes from this to the gamma n bit of advice for that particular function f for that particular location. I'm not explaining it well, am I?
No, what is not clear for me, why you say that you construct a universal string, a universal DNF, and then fix some bits. Why just you do not take the circuits for computing the restrictions and putting them inside?
Yeah, that's what I'm gonna do. Yeah, you can do that. I think it's about the same.
Yeah.
It's about the same. So what you actually do, you take a circuit for computing those restriction functions, and you just do the naive things like DNF or CNF thing, plug it in, and the size will be roughly the size of the truth table. And you use those circuits to plug it into D. Yeah, okay. So then in the distinguisher D, you had some positions there which were just like inputs, and now those positions will be fed through from the DNF circuits of like exponential size. And that will increase your size D to something bigger, because before it was just input, now it's circuitry coming in to give you input to D. So it decomposed with DNFs. Yes, okay. Was that the question, or did I answer it?
I mean, what confused me is that once you fixed, I mean, there's this one thing you want to keep free, this one S.
Right, exactly.
S set, so this stays completely free. Then you have all the other ones which have some bit overlap with this.
Correct.
You want to keep, I mean, the thing is, if you now want to make a truth table, then like the total sum of all the bits that these depend on is already like,
No, but you do it individually. No, you do it individually for each one.
individual, okay.
Yeah, so just a single one, say the first one, F, first occurrence of F.
Each of them gets its own truth table.
Each of them gets its own truth table.
Only depend on very few bits.
That's right. So it has a small truth table. Second one similarly has different, but also small truth table. And as Sasha was saying, you can forget about the truth tables and just do the simple circuit like DNF and plug that in for the first, and a different DNF circuit will be plugged in for the second, and so forth. Good.
Okay, maybe it's time to ask again. Who believes that he or she understands the argument more or less, not the parameter, but just the scheme?
There was a decrease. Yeah, honestly, like I've seen this so many times, and I studied this so many times that it kind of becomes obvious after you see it 1,000 times, but each time I have to explain it to somebody, I realize that it's very non-trivial. So.
But at least the construction, how this generator is clear.
Yes.
Just the details of what you fix and when you fix and what happens with the circuit and so on.
Yes. Very good. So the result that you get, which was a result from the original paper by Nissan and Wigderson, is that if you have a function f computable in exponential time, so you have a uniform exponential time algorithm computing this family of functions for each input length. You have a function associated with the input length, and all of them are computed uniformly by exponential time algorithm. And it's a plausible assumption that this collection of function is exponentially hard on average with respect to exponential size circuits. Okay, so the runtime of E is like 2 to the 100n, and you say that the function is still hard with respect to circuits of size 2 to the n over a million. Okay, there's still a gap. Okay, uniformly have more time, non-uniformly have less size. So it's plausible that in uniform to the million n time, you can compute something which cannot be compressed non-uniformly to less than to the n over a million. Okay? Which is the same as exponential size circuit lower bounds, as I will mention in a second. But if you assume this somewhat plausible assumption that you have exponential size average case hardness for some function in E, then you get that Nissan-Wigderson generator works and it's computable in time polynomial in its output size.
Why is x twice here? So what is x
Oh, yeah,
part
so-
not the same as not trackable by
X part means that this advantage over 1/2 is like exponentially small, and X size is that the circuit is exponential size. Good.
And it's important that the exponent in the existence is bigger than the.
Very important, otherwise it's false.
Yeah, yeah.
Otherwise it's trivial. The assumption is false, so
It's resistant against linear size circuits.
linear size circuits, correct. Yeah, you can play with polynomial in the output size, but it's by padding can be reduced to linear size, so it doesn't matter. Okay, so good. Now, you can make this assumption a little bit easier to state and maybe a little bit easier to work with by going from the average case hardness assumption to worst case hardness assumption. And this is done by using special kind of error correcting codes, locally list decodable ones. Don't worry if you don't know these terms, but there's some way of encoding the truth table of a function f such that the new encoding will give you function f hat with the property that if the old one was computable in exponential time, the new one was still computable in exponential time. And the other property is that the encoding is pretty efficient in that if you had a function on n-bit inputs before, then you have a function on cn-bit inputs now. So it's basically the same number of inputs, but now the new function f hat has error correcting properties, meaning that if you can compute f hat well on average, then you can compute the original f in the worst case exactly. Okay? And by using special error correcting codes, like algebraic ones, Fried-Mahler and Hadamard, and I'll talk a little bit about Hadamard codes later. I think Bruno already mentioned Hadamard matrices in his talk earlier this morning. I'll talk about Hadamard code tomorrow. So using some special error correcting codes, you can achieve this with the property that if f hat is easy to compute on average with advantage epsilon by size S circuits, then you can decode and compute the original f exactly everywhere, and the size increase you pay is going to be only polynomial in S and the advantage 1 over epsilon. Okay.
So what we are trying to do is to weaken the assumption that f is difficult.
What we're trying to do is to get this theorem. If E requires exponential size circuits, which is much simpler, cleaner to state, then you have a PRG as before, from log n truly random bits to n pseudo random bits, secure against linear size circuits, and in particular, you can de-randomize randomized algorithms and show that Vp is equal to P.
So what does it require size?
To the omega n, omega n. Yeah, exponential size circuits. So now there's only one exp. The second x, the advantage thing, is taken care of by error correcting codes.
Do you mean here if there is a function in E that requires?
Yeah, it's kind of what I mean by this. It's a shorthand for what exactly, what you say. For every n, yes. Yeah, like if you have infinitely often, then you have a generator which works infinitely often. I'm trying to sweep those things under the rug. But when I say things like this way, E requires, I mean almost everywhere. Yes. Is that good? Actually,
And which is resistant against what?
linear size as usual. Size n tests circuits. Yeah, the usual. Your tests are always assumed to be linear size in the output length, just for simplicity. So linear size circuits. And you can do padding, and like if you have polynomial size circuit to full, just pad things up, and you still get some bigger constant in front of log n as the size of your seed.
And so we claim that BPP is equal to P.
under this assumption. So if you have the circuit lower bounds like that, then you have a PRG, and as a consequence, you have BPP is equal to P. And I just wanted to point out that this is an equivalence here. So this then can be replaced by if and only if. So if E has large circuit size, then there's a PRG from log n with exponential stretch, and conversely, computable in time polynomial in n. And conversely, if you have a PRG with exponential stretch computable in time polynomial in n, then you have high exponential circuit complexity function computable in E. So you have equivalence between the existence of hard function in exponential time and the existence of exponential stretch generator.
But not the equivalence to BPP.
No. I was very careful to replace that by not there. The equivalence of BPP equal to P with some kind of assumption is an interesting open question. There has been some progress recently, like related to like uniform randomization that I'm not going to talk about. How much more time do I have?
How much do you, we can stop at any moment when you're tired.
Yeah, I think it's going to be good. So like a couple minutes maybe. I'm pretty much at the stopping point, but I just want to introduce some cool idea. Play to win versus play to lose that I mentioned before. So what do I mean here? Remember the construction of the Nissan-Wigderson generator based on the function f. So G superscript f. Its generator using designs and assumed function, hard function f. Well, it doesn't have to be hard, it can be any function. You can still do the construction, and you'll map L bits into K bits. So now you don't think about this as necessarily a pseudorandom generator, but some kind of generator, and it has some properties. Now, for the randomization purposes that we had in mind before, like historically, that's why these generators were defined, we tried to win, we played to win. Winning here means that we want to get a generator which is not breakable, which cannot be broken, which is pseudorandom. Why? We want to fool randomized algorithms, we want to randomize them, that is why. How did we achieve this? Well, we were very careful in selecting the parameters. And the important parameter to watch for is the size of the output of the generator versus the inherent complexity of the function f that the generator is based on. You want to make the output length k smaller than the circuit complexity of f itself, because that's what allows you to get a contradiction. If you have a distinguisher, which is linear in k, which breaks the generator, then you have a circuit of size roughly k, which computes the function, and if the function requires circuit bigger than k, you have a contradiction.
So resistance is always against linear in k.
Yes, 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 yes. It's always linear in k. Yes. So if you choose k to be smaller than the complexity of f, you get a generator which works, which can be broken, and you get the randomization of BPP and other stuff. Maybe you want to break the generator. So you want to play to lose. So if you choose k to be larger than the circuit size of f, then the generator G sub f can be broken if you can somehow measure the complexity of the output of the generator. Like say you can measure the circuit complexity of the string produced by the generator. And intuitively, the function f has some circuit size. The output of the generator, the string of length k, if you think of it as a truth table of a function, will also have some circuit complexity. But the NW construction outputs something which is basically evaluations of f on some carefully chosen substrings of the seed. So intuitively, the circuit complexity of f is inherited by the circuit complexity of this string, which is the truth table output by the generator. Okay, so you can make things more precise, which I'm not going to do now because I'm running out of time. But if you choose k to be large enough, you will argue that the circuit complexity of the output of G of f is going to be smaller, sufficiently smaller than k. Which means that if you can compute the circuit complexity of a given truth table, you'll be able to break this generator. On a random string, k-bit random string will have maximum circuit complexity, roughly about k. But the output of the generator on kind of easy-ish function f will have much smaller than K complexity. So you can distinguish the outputs of the generator, because they have small circuit complexity, from the truly uniform random strings, because they have huge circuit complexity. So your circuit complexity algorithm, assumed circuit complexity algorithm for minimum circuit size problem, that I'm going to talk about version of later, allows you to break this generator. Now, why do you want to break the generator? Because the analysis of the generator being pseudorandom is very constructive, meaning that if you give me a distinguisher, which is an efficient algorithm for breaking the generator, then I can do this reconstruction procedure and give you an algorithm, a circuit for computing F itself. The proof of correctness of NW that I told you is constructive enough for you to be able to recover a circuit for F from a given distinguisher D. Okay? So this gives you a way to learn functions F you want to learn by plugging them into the PRG construction, making sure to set the parameters right so the generator can be broken by circuit size estimation algorithm, and then this gives you a learning algorithm for functions F of relatively small circuit complexity. Okay? So you get the learning algorithm from the existence or assumed heuristic for estimating circuit complexity of function or time-bounded Kolmogorov complexity of function, whatever you want to assume. Okay?
So you say if this MLSP is
Yes.
simple, then what? We can
If you have polynomial time algorithm for MCSP, then you can learn all functions of polynomial circuit complexity on average. What?
What does it mean, learn function?
Okay, so learn function means that I will produce a circuit which agrees with your function almost everywhere. So it's a standard computational learning setting of Les Valiant, where you have access to your function to be learned. And in this setting, you need to have membership queries. So you don't not just random examples, but you can query polynomial many points of your choice to this black box function F. And after polynomial many steps, you spit out a circuit which agrees with the function on all but inverse polynomial fraction of inputs. Yes.
Where did you, so you say if you can compute, and so you need it here somehow, the fact that we can compute this.
Yes. Because this algorithm for MCSP will be my distinguisher. And so once I have a distinguisher, then I can run,
Distinguish what?
distinguish the output of the generator from the uniform distribution. So this MCSP heuristic will break this generator GF.
Because it will,
I will set the parameters.
It will see that, from the table it will see that the function is simple.
Yes, exactly. Yes. Okay. So of course, we don't believe that circuit complexity can be estimated efficiently. However, there is a setting, it's going a little bit more than 3, but it's an interesting discussion. So there is a setup where this can actually be used. Okay, so in general, you cannot estimate circuit complexity well, but for like restricted classes of circuits, like constant depth circuits, even with mod prime gates, you can actually estimate the circuit complexity of truth tables and distinguish those which are computable by small constant depth circuits from random ones. And in that setting, you do get efficient MCSP algorithm, which comes from the work of Razborov and Rudic on natural proofs for analyzing like circuit lower bounds for constant depth circuits. So they managed to show that there is some kind of MCSP average case algorithm for the special case of constant depth circuits with mod prime gates, which means that this approach does give you a learning algorithm for constant depth circuits with mod p gates. And it will run in quasi-polynomial time. And I think this is a good place to stop. Thank you.
Questions? I have one very naive. You mentioned at the beginning that for some constructions, for random proofs of existence for error-correcting codes, for expanders, for extractors, whatever, there exists some derandomization.
We have explicit constructions.
Yeah, explicit constructions. A naive question is, are there constructions that make a kind of partial derandomization, such that, let us say, error-correcting code becomes not explicit, but it is defined by a small family of parameter, something like a seed or pseudo-random generator?
Yeah. I believe we have examples of randomized decoding algorithm, at least, for error-correcting codes. I think maybe what you're kind of hinting at is the notion of pseudo-deterministic algorithms that Igor is going to talk about more in a couple of days, where you construct a unique object, but your construction algorithm flips random coins. And yet the object output is still unique. It's the same for whatever random coins you flip. So that would be like partial derandomization, where you allow randomness, but you still create an object in a unique way.
Yeah, let us say for an error-correcting code, it could be that the object is not unique. But if you want to use a good error-correcting code, you need to embed in your mobile phone a short seed for the Nissan-Wigderson generator.
Yeah, it's possible. Like in general, of course, Nissan-Wigderson generator only works if you have hard functions, which we don't have. But in principle, you have a randomized construction. If you can verify that the object constructing is good efficiently, then you can always fool it by using pseudo-randomness instead of true randomness, and then you get exactly what you just said. You just use the seed that will give you the randomness exponentially bigger than the seed, which can be used, and it will be unique. If you fix the seed, then you fix the output of the algorithm, because this randomness is going to be fixed by the fixed seed.
At least so far, we don't have industrial applications of Nissan-Wigderson.
As far as I know.
I think that this issue, Andrei, is not because you can't tell by looking at a code whether it's good, right? Or maybe you can do it approximately, but certainly.
Yeah, it's a hard problem.
Exactly.
I guess that in coding theory, in applications, sometimes they just sample a random matrix.
Right.
But here, it could be better to sample a random seed.
Right, but then they pray that the code is good, right? They don't actually have a test that they can run after to check. That's actually, no, I believe that, there's some hardness to it.
Yeah.
Yeah, and there is this population hashing. So, for example, there are constructors of expanders using pure randomness, which are very practical, using tabulation hashing, which is done by Toruk and Petrashko. And they are very, very practical.
So if you can summarize the discussion for the recording. Okay, let's.
Yeah.
Maybe next time.
It's hard for me to compress it like online.
Repeat what was said in the last remarks, if they are.
Yeah, so there was some discussion of like, can you use PRG, like Nissan-Wigderson style PRG, to build practical error-correcting codes? And I think the answer is like, we don't know. And Bruno says that you cannot really test if the code is good or not. Testing random code as being good is kind of a difficult problem. And then I didn't quite catch what Marius was saying.
And same for expanders.
For expanders.
So it's not a deterministic construction, so you still cannot check efficiently if I graph an expander. But you can replace the complete random construction by using tabulation hashing, which is using fewer random bits and it's very fast.
I see. Okay, so it has a partial derandomization.
Yeah, I think it's what else.
Yeah, so there's partial derandomization for expander construction.
Any other questions? Okay, let us thank the speaker.
Thank you.